way more than a minute, so let's get started. If you have questions, just feel free to raise your hands or unmute yourselves. Okay. So today we're going to talk about how to calibrate spectral line observations taken with the GVT. So we're going to be covering a bunch of things, what the GVT measures or single dish telescope, how we calibrate these things, what are some different brightness scales to which you can calibrate to, some observing calibration strategies we can be using during this session, or that you might already have chosen one for your own projects. And we'll end up covering a bit how you would go about reducing your data. Some of the things we won't be talking about, but which are very important, is how to deal with RFI and calibration without noise diodes. That would be if you're a project at 3 mm using Argus, for example, that would be really relevant. I'm sure Dave and Annika can explain that much better. So that's going. So in terms of what the GVT measures for a single dish telescope, well, what we're measuring it's mainly power, right? So we have incoming radiation. This radiation induces a current into the receivers, and that current we measure as voltage, and then we basically compute the power out of taking the square of that voltage, and we end up with something that looks like the left-hand side, a power as a function of frequency, meaning we'll have a value of power for every channel of frequency gain. And in terms of how this relates to what we're interested in, the radio astronomical signals, we can use this simple model of how those things are related, where we have a multiplicative factor we call a gain that depends on the telescope and electronics and so on. And then in the square brackets are physical quantities, dA, or we call the antenna temperature, which is what we're after, and then a system temperature, which is basically all the things we don't care about. So let's start with the stuff we don't care about, so we can get it out of the way. So the system temperature is a combination of all the things that you may not be interested in. CMB, I guess, is the one that's a bit dubious, depending on what kind of science you're doing. So we will include the CMB. It can include any background sources which you're not interested in. We'll include the atmosphere, spillover, because you're like illuminating a bit over the edges of the dish of the telescope. It includes standing waves, which GVT has very little of because of its offset design. It will also include the receiver itself, and depending on if you're using a noise diode or not, that also goes into your stuff, into your system temperature. Basically, everything that you can think of that's not your actual source, you can call system temperature, and then the calibration basically reduces to finding a way of removing the gain and the system temperature from your measurements. So that's we can do that in general if we assume we can observe a region that's empty. So there's no astronomical signal. It's only the stuff we don't care about and the telescope itself, and we call this a reference position. So in that ideal case, one can see that it's pretty straightforward to subtract one from the other, and we get rid of the system temperature, we still have the gain. We can divide one by the other, and we end up with something like this, but we're still, when we do take the division, we basically have the system temperature back, but we can measure that by using some clever tricks. And this would, in the end, give us our antenna temperature plus some variation on the system temperature, right? Because no two positions in the sky are the same. So there's always going to be a small difference there. So in principle, one could compute the system temperature from first principles, meaning like we know what the CMB is, we know what the background is, we know the telescope geometry and like characteristics, so we could like model how all these things come together to give us a system temperature. But in practice, we have these little things called noise diodes, which uh, basically we're injecting a signal of unknown strength into our system so we can infer most of these quantities, if not all of them. So how does that work? Well, assuming again that we're looking at the blank sky, we have our gain times the system temperature, and then we fire the noise diode, right? Now we explicitly put it out here, and we end up with this new quantity, or we fire the noise diode. And again, we can just do some algebra to solve for the system temperature, and we see that the system temperature is then equal to the temperature of this known source of power times the ratio between the things we measure in this form, right? And the whole trick here is that we can measure this Tcal value or the temperature of the noise diode either in the lab or using a source of unknown flux density. So then we can solve for the system temperature and then put that back into our previous equation to get the antenna temperature, which is what we care about. So in practice, this looks a bit like this. We might have one of our receivers. We have the first stage of amplification, right? The most important one. And then we inject a noise diode along the signal path. And then all the rest, basically it shares the path with our astronomical signal. And that all goes into our recorder or backend, right? So that's basically what we're doing. And this is all inside of the receiver itself. And like I mentioned, we can measure this in the lab, right? But as most things with time, they change. And here's an example on the left of the diode temperature of one of the receivers at Arecibo, the L-band receiver, and we can see that it changed by roughly 20%, I guess, over the course of 6 years or so. So it's important to remeasure these things often. So that would be, I guess, my first recommendation for you is if you're carrying out observations, well, ask your project friend, hey, when was the last time the temperature of this thing was measured? And if unsure, or if your science goal has a very uh, requires of high accuracy, just observe a source of a known flux density and rederive the noise diode temperature. Here's another example of this. This is with data from the GVT, where this was a large project that spanned a couple of years, and they compared basically what was the temperature that the observatory was giving for the noise diode versus what they were measuring, and they arrived at a ratio of roughly 1.2, which there's a lot of scatter here, but the data is consistent with being constant with time. So there was a drift, but then it kind of stabilized, but still 20% difference. So that's the kind of things you need to be thinking about as you're devising your observing project and thinking about the data reduction, right? Can you do with 20% accuracy in your absolute flux measurements, or do you need to do better than that? If you need to do better than that, then you should be measuring the noise diode, or at least consulting with the observatory staff to make sure that the value is just to know how accurate it is and when was it last measured. Another important thing to remember is that it's frequency dependent. So in this case, we're showing the noise diode for the X-band receiver between roughly 7 and 12 and something gigahertz. And you can see it changes quite a bit, right? Can be roughly 1.25 Kelvin all the way to 1.75 Kelvin. So that's another thing that's important. If you are doing, for example, broadband spectral line measurements, you do want to measure this thing yourself using the same setup you will be using for your science, because then you can have a more accurate representation of what this is, which leads to better accuracy overall. So the nice reference here by Benjamin Winkel, where he shows basically what kind of uncertainties you can expect just if you ignore this frequency dependence in a more simplistic case. But it gives a good idea of what to expect. Now, I've spoken a lot about this, but well, like maybe so how do we do it basically? Um, if you're observing at low frequencies, so let's say below 30 gigahertz, there are a bunch of sources which are quite stable in time, known as the Perley and Butler sources, I guess. It's the most, yeah, it's one of the most the best catalogs. But basically, you know the flux of these sources as a function of frequency. You can go observe one of these sources, compare with what you're measuring, and you assume that all of the difference comes because of your noise diode is mis miscalibrated, or because the temperature that's reported is different from what it's actually doing. Um, the ones that you should pick should be stable in time in that case, because the Perley and Butler for most sources only gives like a snapshot, right? So if things have changed with time, uh, it won't be useful. If you're observing at higher frequencies, most sources are time variable. Luckily, the ALMA does regular checks on those sources and provides um, basically fluxes for all of the sources. You can cross calibrate against those. And very importantly, the source you're observing must look like a point to the telescope. So it must be smaller than the telescope beam. So otherwise, you need to take into account also like how much of the source you're looking at or what part of the source. Things can get complicated pretty fast. So just use a small source. And in Perlian Bottle, there's plenty of good sources all over the sky. It shouldn't be an issue to find one during your observations. Also, a slightly older one from Ott, but it's also good. The frequency range might be slightly less where, where they report their flux density values, but it's also a good reference to use. So far we've spoken about how to get this quantity, right? TA, the antenna temperature, um, which is a very fine measure of things. However, it's very important to note that this depends on the telescope and the observing conditions, right? Yeah, it's kind of like hidden in the names. Temperature the antenna is seeing. It's not really like the source temperature or something else, right? Um, so there are ways in which one can account for some of these extra subtleties, like the telescope itself or the weather conditions to arrive at a measure that's more independent of them. So the first thing that one should do is correct for the effects of the atmosphere, right? If we're observing at 22 gigahertz, for example, there's this big, deep absorption feature from water. So we want to take that into account. Um, and we do that, right, going to this scale called, which here we call TA prime. So that's the equivalent antenna temperature above the atmosphere. So we're only correcting for this absorption due to the atmosphere. That includes knowing the opacity at zenith and the air mass. The opacity at zenith is something that the observatory can provide for you. There's some tools you can use to get it. You can ask for it. In the air mass, there's some, yeah, some approximations, which is pretty simple. Like I forget exact functional form, but something like 1 hour sine. That's usually pretty good for elevations above 30-ish degrees. Then we can be a bit more, go one step further and try to say, okay, like we're gonna go above the atmosphere, and we also only want the power that's being collected in the forward direction of the telescope, right? So ignoring any uh, spillover. And we correct for that using this eta L. So we take TA prime divided by eta L, which for the GT is almost 1. And we arrive at this quantity TA star, we call. And this is usually, yeah, pretty, like, this is usually like one of the the best you can do without going into like a lot of detail. And then for sources, and this is pretty independent then from the telescope. And then depending on if your source is extended or not and whatnot, you might also want to use something like the main beam temperature, where you're basically saying that this is just the temperature within the main beam of your telescope. But that again, that depends a lot on the source geometry and what your science goals are. And here are some values for this main beam efficiency and where to find them in case, in case that's actually what you need to do. And there's this very nice guide put together by Emily Morelek about temperature scales and more details about these things. I'll keep going then. Again, the zenith opacity provided, and you can see there's a guide explaining how to get it from the data reduction machines using Clio and other tools. But again, if you just want to know it, you can just submit a help desk ticket and just tell us, hey, what was the zenith opacity at, let's say, 30 gigahertz yesterday between noon and 6 p.m. And we should be able to give you those values. You can carry out your data reduction. So, okay, we've covered a lot, right? We spoke about what we're measuring and how we wanna and how we can write observer source and a blank portion of the sky, this reference to calibrate our data, and how in doing so we want to know well, we're going to use these noise diodes or something equivalent if you're observing at higher frequencies, like a Bain, which is effectively a noise diode that which is just like a mechanical noise diode instead of electrical. And then, but then, yeah, how do we do this in practice? These measurements, right? So we kind of assume that from now on that you know the noise diode well enough, but then we're interested mostly in being able this difference between the on source and the reference being as good as possible, meaning like this delta in system temperature, we want to make it as small as possible. So how do we get there? There are a bunch of different techniques we could use. One is we don't do any switching at all, so we just observe our source, or stay on our source, and if the conditions are right, meaning we know the source well enough, and we know like where we're expecting our spectral lines, and the spectral lines are like narrow enough, or we know them like super well, and the telescope behaves in a nice way, we can just do something called baseline subtraction. Put an example out. Then I guess position switching is like very versatile. So you don't need to know like your source as well, but it does require moving the telescope, so there's time wasted in that, and you also need to observe a reference position, right? So there's time lost in that too. So it's very versatile, but it's more costly in terms of time. So talk a bit about that too. And there's also frequency switching, which has also, of course, pros and cons. Pros, you spend your time on source. Cons, you don't get a continuum measurement, and under certain conditions, it's not going to work that well. But we'll give more detail about that. So let's start with baseline subtraction. And here the idea is that you know where your line is, you know roughly how broad it will be. So then you can say, well, and your telescope has a smooth frequency response, meaning there's no large, let's say like stepwise functions in there or breaks. There's not a lot of RFI either. Then you can say, okay, like let's consider only channels where there's no signal, and let's model this, let's say, with a polynomial. And then you can fit a polynomial to those line-free channels, subtract it, and end up with something that looks pretty decent. So yeah, so this only works on very particular cases, right? You need to know a lot about your source. You don't get a continuum measurement because basically the continuum is hiding here, but if you're fitting a let's say a baseline model to all of that, then yeah, you lose that information. And it has the advantage that you can stay on your source as long as you like, because you don't have to go somewhere else to measure this reference power. Okay. Next one, position switching using on and off. This is very simple. The idea is you observe your source, you move the telescope, you observe the reference, you do the math. Right, so in this animation, it's showing the telescope headbanging. What you really want to do is move it sideways so you keep the elevation constant. Because moving in elevation, you change a bit how the structure, the shape, and how it's illuminating the ground. So it's not the best. But again, when you measure towards your source, you have the gain, the antenna temperature, and the system temperature. When you measure the reference, ideally just the gain and the system temperature. So that's the tricky part, finding portions of the sky where this condition is satisfied and these two system temperatures are as close as possible. So there's a very nice tutorial on this link explaining how to set up the telescope and how to do the observations and how to reduce the data. Also data reduction guide here and what you can expect, for example, from something like this. A position switch observation at L-band 1.4 gigahertz with the GBT. It's pretty good. Like if you look at the spectrum, like the frequency response is pretty flat besides this spectral line. That's exactly what you want. Then you know your line is well defined and all the rest is pretty flat. So it's a pretty nice measurement. So some notes about this, right? The off region should not have emission or absorption in spectral lines, or if it does, at least it shouldn't be interfering with the line you're interested in towards your target, right? You don't want to imagine if your off position had a line, let's say half the amplitude of this one on the same position, then when you do the on minus off, you're basically subtracting half of the power, so then you don't get a clean measurement, so you don't want that. Right, the telescope, the gain, and the system temperature might be changing. Let's say it's a cloudy day and you're observing at X-band or higher frequencies, so 8 gigahertz or above. The clouds are rolling by fast. You want to keep up with that, right? Because if there's a cloud, well, you're measuring, or well, not a cloud, but if there's something affecting your measurements towards your own position that it's not there when you measure the off position, you're gonna get a slightly different answer. So you wanna know often enough. And again, the off region should be chosen to minimize differences in the system temperature. So that's why you don't wanna change elevation, just azimuth if possible. You don't wanna go like, well, you wanna stay as close as possible because then you spend less time moving. Yeah. Again, the advantages, you don't need to know that much about your source. On the drawbacks, you lose time because you need to move, you need to observe the position. Because you're observing two different positions, the difference between the power towards your source and the reference is not going to be equal. So there might be residual things, so things might not look as clean as here. But there's a lot of experimenting to be done there. And again, the off region also chosen with care. This also applies, I mean, because this is the only technique which will be, well, the position switching is the only method we will be covering that also gives you a continuum measurement. So if you're also interested in continuum, it's also good to keep that in mind. Well, there were two other flavors where are a bit less costly in terms of moving the telescope, but also have limitations. One, for example, is nodding. So you node your source between two beams or feeds. It's the same idea, right? Your source is this pink circle, and these inverted triangles are your receivers or horns. And you just put the source in one and then the other, and you keep linking back and forth. The advantages, you're always observing your source, either in feed 0 or feed 1. Drawbacks, this only works if the source is smaller, right, on the separation between the feeds. Let's imagine the pink circle was bigger than both, then when you move in one or the other direction, um, you either cannot entirely observe blank sky or you don't observe the same position of the source. You need a receiver with at least two horns or beams, and there's some overhead in moving the telescope, right? So that's how you make sure that the source is in one feed or the other. As an example of a feed that can do this, in the GVT, we have the K-band focal plane array, which is a 7-beam, 7-feed receiver in an hexagonal pattern. And the beam separation on the sky is roughly 1.6 arcminutes. So you could use the KFBA2 nodding. There's yet another one called sub-reflector nodding or sub-beam nodding, where you also have two feeds, but now instead of moving the telescope, you move the sub-reflector. That's this inverted parabola here. And when you rotate the sub-reflector, basically you're directing the beams to different positions, and you can do this so that one beam observes the source, the other observes blank sky, and you alternate between these two things, right? You could even do this with a single feed, but then you don't get the same advantages, right? But all time is spent on source. And again, this will only work if you can move, if your source is smaller than what you can move the beams, the separation between beams. And just to show another, the GVT receivers, we have the 4 mm receiver or W band, which is also a two-feed system. These are the two feeds. The thing in the middle is for calibration purposes. And in this case, the two feeds are separated by roughly 4.7 arcminutes. And that covers position switching. Let's now quickly jump to frequency switching. So here the trick is we're not going to move the telescope, we're going to move the frequency, right? So when we have the signal coming in, we saw before, we mix it with a local signal, the local oscillator, so that then we can sample it at our backend or recorder, right? So if we switch slightly this tone we use to down convert our signal, we can shift things. This is effectively shifting things in frequency, right? So if we have a spectral line, it will appear here or there, depending on how much we change the local oscillator. And then we can subtract one from the other to basically remove all the stuff that's not the signal, not the line, right? So you would end up with something that looks like this. You have your line, you have the line ghost, we call it, right? Where you have subtracted it, and all the rest will be more or less flat, depending on how much you had to move in frequency and the characteristics of the telescope, right? So again, you don't get any continuum because you're subtracting everything. And you do need to know where your line is going to be and roughly how broad it's going to be, right? Because you don't want to, again, be subtracting, chopping off the wings of the line when you do subtraction. Advantages, you don't have to move the telescope, right? You're just switching in frequency, so you're always getting signal. That's good. It's pretty fast, right? Because you're only doing electronic switching, so you can flicker this thing pretty fast. I forget what's the limitation there. And the limitations, like we said, you need to know your source. The baselines might not be as clean as with frequency, as with position switching. I mean, sometimes it's better. It all depends on how you choose things and whatnot. So that's one of the things. If I were attending the workshop, I would be interested in comparing those two methods, for example. And you don't get continuum. Okay. That's a lot of theory. Well, maybe not so much theory, but a lot of yeah, of yeah, a lot of things to listen to. And one more, the last part of this talk is gonna deal with data reduction. So basically, we saw the theory, right? This is the power it's coming in. This is the model we're using, where the power is equal to the gain times the antenna temperature plus the system temperature, right? Measure an on and off. We, sub we subtract one from the other. I mean, a signal and a reference. We subtract one from the other and divide by the other, multiply by the system temperature, right? We saw that we need to know if we're using a noise diode, we need to know its temperature, right? And how we can measure that thing roughly. And then some of the techniques, observing procedure methods that one can use to measure the signal and reference. And now then we jump to the last part. Okay, so you did all of that. Let's say, how how does my data look like, and how do I like work with it? Like, because GVO doesn't give you sort of like data products, right? It's a very hands-on everything. Come here, learn about the telescope, learn how to carry out your observations, and then reduce them yourself and make your own science data products. So like Larry mentioned, we're switching to the use of Dysh. So in a sense, you'll be guinea pigs. It's not the first time we're using it during a observer training workshop. So uh, yeah, don't feel like we're like putting you through something particularly bad. But just keep it in mind, and mainly because it's also part of my job, I need to. I would like very much to ask you, like, if you have any feedback, positive, negative, or things that could be done differently. We want to know. There's still some room to change things around. So yeah, just I guess that's the how to preamble this. We're still working on it, and we want to know what you think. So it's Python based. My previous one was written in IDL. I would do a show. I will ask for a show of hands, but I cannot see all of you. How many of you have used IDL? But that's fine. But maybe put in the chat to humor me. It's only intended to be used for spectral line data reduction. Maybe that will change in the future, but for now, that's it. And it's designed specifically for the GBT, even though the goal is for this to also support observations from other telescopes eventually, uh, if anybody wants to do that. So it knows, like, if you tell it, if you observe with the GBT and you said like, oh, do a node for a sub-beam node, the package knows, okay, like this is what you mean. This is how I should calibrate that. Here's your data, calibrate the data. It's already available in a GVO, but you can also install it. Oh, and I should have changed this. This is not actually the way we want you to do it for now. But the idea is that you can install it in your own computer if you want. That the command should be slightly different if you want to use the latest version. So it's like because it's in continuous development. This won't give you the very latest version. But here's the documentation, and there's the proper way of installing it to get the latest version. It's in there, as well as tutorials and examples. And if you have comments about those, please also let us know. Things are not clear, or if you want to know how to do something different, uh, I would love to hear your thoughts. So if you're at GVO, you can launch it just typing Dysh in any of the terminals, and you will be welcome with something that looks a bit like this. So you'll get some information about what version of Python and IPython it's using, and then a banner specifically for the package, welcoming you, telling you where to find documentation, where to report issues, and yeah, it will preload some methods and libraries for you, and then it's very much an IPython command line prompt. It's just IPython with a banner, so to say, and some preloaded modules. So if you're familiar with IPython, excellent. Because it's just a Python package, you can also use it in a Jupyter notebook. I'm not going to give examples of how to do that here, but if you're familiar with Jupyter notebooks, there's a tool called Dysh-lab, which will basically launch a Jupyter notebook within GVO hosts. And you can then navigate with your web browser to the address and basically work with your notebook. If you're doing, because we're doing everything remotely, you will need to tunnel uh, basically for your local computer to see the host, the Jupyter server on the GVO host. But we can talk about that, or I can point you to directions on how to do that later if that's what you would prefer to. But the functionality is roughly the same. So okay, so that's the first part. That's how you launch it, and it's just either an IPython terminal or a Jupyter notebook, then getting help because it's built on, it's just IPython, right? You can just use IPython commands to get help. Object question mark or object double question mark. That should work, right? And then how you load your data. There's three ways in which you can load your data. So let's say you're observing tomorrow night and you want to have a look at your data as it's coming down, make sure everything is looking fine and nice. You can use the command gvt online, and that will automatically connect to the latest observation that was written to ISC, and it will auto-enable auto-reload of that data, meaning every time new data gets written to that observation, it will automatically update the data. This might be a bit slow, but it does it. If your project was observed already, say last month, or yeah, within, well, up to, I guess, 1 year-ish, you can use GVT offline, and then you give it the project code, or I should say session code, and it will load the data for that particular observing session. And let's say you're at home, you downloaded your data, you submitted a ticket to a help desk saying, hey, I want data for this source at this frequency in this mode. And you have it at home, you can use GVT feeds load and point it to the data that you got from the help desk. Or you can use the same here. If you copy your data to your own stretch area, you can give it the full path and it will find it, right? And then all the data contents are then stored in this variable called sdfeeds. That's basically your entry point to your data, right? So you can print a summary of your observations using .summary. And this .summary has a bunch of options. For example, you can tell it to be verbose. And the way the observations are written is basically a long table with many columns, but like a rough description of this is you get one row for each integration that you observe with the telescope, right? So each row can represent a different frequency, a different calibration state. For example, if you're firing the noise diode, you will get one row without the noise diode, one row with the noise diode, without, with, and so on. If you're observing with multiple beams, one row can be one beam at one time, second beam, same time, first beam, next time, second beam, same time, and so on. So if you say verbose equals true, it will print all of that. It can be quite lengthy. You can specify the observations are usually grouped into scans, meaning like if you say, let's do an on and off observation, while you're on source, that's one scan, while you're off source, that's another scan. So you can say, okay, I just care about this particular scan because this is where my target was. You can tell it, okay, just that scan. The summary is contains a bunch of columns, which we thought were, well, we were told they were like good columns. But if you want to add other columns, you can say, hey, show me more information about what's this thing, binary table. You can do that. Of course, for that, you would also need to know that there's such a table, such a column, and what that column, and then to interpret the results, you need to know what the column is. So there is a description of the columns available in your data products, the raw data products in the Dysh documentation. And this one we still need to work a bit on, but so let's say you're observing at L band, or let's say you're observing with Argus. You have 16 feeds, and then you, on top of that, you can have like multiple spectral windows. Argus has a single polarization, but 16, let's say, times, let's say you used 8 spectral windows. So some that's, you can do that. That's a lot of combinations, right? And you need to know basically the numbers for each one of these things, like spectral windows 1 through 8, beams 1 through 16. And depending on how complex your observation is, you might end up with weird combinations. So you only have one beam with one spectral window or IF number, IF num, and so on. So you can ask which numbers are present in your data by using this command you show. But we need to improve that. Okay, so then in Dysh, what's something that's important to know is how the data is structured and how it flows between like, okay, this is your raw data, you get your calibrated data at the end of it. So this diagram tries to cover a bit that flow, right? So again, let's say you're interested in measuring the 21 centimeter line towards an extragalactic object, and you're going to use on and off. And because of how things change, right, you're going to observe on 5 minutes, then off 5 minutes, and you're going to do this for like 3 hours. So that's all you're doing for 3 hours. On 5 minutes, off 5 minutes, on 5 minutes, on, pum, 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 pum. So you would end up with lots of scans, right? All of the same object, which then in the end you want to calibrate each one of these scans, right, with the corresponding off, and collapse all of these into a single calibrated spectrum, because the astronomical signal, the antenna temperature, well, yeah, the astronomical signal should not have changed. So we will have the data in our SD fits, we call it, which is basically this GBT fits load object we were speaking about before. So yeah. So each one of these, even though they have different names, they all return what we call this GBT fits load object, which contains an index, a selection, and flags. Right? The index is just telling us, okay, this row corresponds to this spectral window, this time, this beam, this source, and so on. Selection is if you wanna, even though there might be many rows and many objects, if you just wanna like reduce that number, like I'm just care about this object, you can select that, and the flags basically, I don't know, like I know these channels were bad most of the time because of RFI, that would be a flag. So then the data flows from this onto a scan block where we can have multiple scans, or it can be a single one. The way we go from this one to this one is using a calibration method. So it can be like get PS for position switching, get FS for frequency switching, and or get node for nodding, right? Two beams, or sub-beam node when we're moving the sub-reflector. Right, so each one of those will give you a scan block, which can contain multiple scans. And then from this, you can time average them. And in that case, you get a spectrum. So you jump from here to here. And this is basically your calibrated data in a way, right? It will have flux, mask, and metadata associated. You can plot it or you can write it to disk. And if you want more control over things, in between, you can extract scans from this scan block. Let's say look at individual integrations. If you want to say like flag some because there was RFI, you can use this to inspect things in more detail, right? And from a scan, you can also time average things into a spectrum. That's roughly the data flow, and I hope it will make much more sense when you look at the examples and when we work with actual data tomorrow. So a few more things you can do, right? So we spoke about the calibration methods. So whenever you want to calibrate data, you need to specify at the very minimum, and depending a bit on the type of observation, you need to specify the spectral window or IF number, IF num you want to reduce, the polarization number or PL num you want to use. And in some cases, you might have also to specify a feed number. Actually, in all of the cases, but this one you don't really need to provide a feed number. So those are the minimum. Then you can also provide additional arguments like scan number. Hey, I only want this scan. Or you can provide a list of scans or a range of scans, then it would work with all of those. And yeah, this all calibrate different types of observations, like I mentioned before. And there's this one which we didn't talk about, which is a more generic version of this thing up here, in the sense that when you're observing with an on and an off, your data get labeled, okay, this was the on and this was the off, and this is a pair and they go together. With this one, get SIGREF, you can kind of like break them apart and, hey, maybe this on, it's they're off, they weren't a good match. So maybe the next off was better. So you can then like break that. Um, and many of these things don't make any sense, but they're this way for historical reasons. But yeah, so we inherited them. Um, so yeah. Um, Again, hopefully this will make a lot more sense when we are actually working with data and going through things ourselves. So again, just to real more things, scan blocks, in the end, are just lists of scans. If you're familiar with Python and with lists, that's just to say that you can slice them or cell index them, right? So we said before you can do this dot time average. It will basically collapse all the rows inside a scan block into a single spectrum calibrated, where you can just select the first scan within a scan block, calibrated time average, give me a spectrum. So you can just look at them separately, or you can do ranges, right? But because this is a list, can only do list indexing, but it's okay. Um, And then scan, right? So we have scan block, it's a collection of scans, and a scan is a collection of integrations. So then inside a scan block, we index, we get the first scan, and then, for example, if we want to get a particular integration, we just get spec, and then the number, 0 being the first integration, so on. Just want to look at all your calibrated data and just return it as a NumPy array. Dot calibrated will give you back that. And you can do things like subtract a baseline or undo a baseline subtraction from all of your integrations in a scan block or a scan. And finally, spectrum objects. So again, like you have all of your observations, you calibrate them all very nicely, and you end up with your data calibrated. And now you come down to like this single entity where you're going to measure the flux in your line or lines, or yeah. So, but you might notice, for example, oh, I don't know, like signal to noise would be slightly better if I could like smooth a little bit things. So there's a smoothing function that can help you with that. Or let's say your on and your off were not perfect match. So there's still some baseline, some waviness left in there. You want to remove a baseline. There's a function for that too, right? So you can specify what kind of model you want to use, a polynomial, Chebyshev polynomial, a Legendre polynomial, the degree, and you tell it, yes, I want to remove it. And we'll hopefully work with through some examples with you tomorrow and the day after. You can average spectrum together, right? So you might have two polarizations or multiple spectral windows which will have the same signal. You want to average them together to reduce the noise, thus increasing the signal to noise. You can average them together, and you can do things like slicing of your spectrum, right? So you would ignore the first 10 channels and the last 10 channels, and you can then compute statistics. Say you want to know what the median is or the RMS, that will give you back a small dictionary with some basic statistics. But because these things are just basically contain NumPy arrays in them, you can do whatever you want with them if you're familiar with NumPy. And some more important things, plotting. You can plot your data as a waterfall. I should have put an example here, sorry, but a waterfall is basically frequency against time. It gives you a visual representation of how things are changing with time. And once you time average everything, right, you lose the time component, so you just draw a squiggly line. So we call a spectrum plot. And well, actually, we can look at, oh, need change my screen sharing, but okay, it's only 4 minutes left. So we will look at some of those tomorrow. Sorry, when we're working with you. And then writing your data, right? So you might want to save only a subset of your observations. So you can, from your GVT load object, you can say write, and you can specify on the call to write. Just keep these particular scans or spectral windows or times. You can do that. You can also save your calibrated data, time resolved, so the scan block or the scans. And you can also save your spectrum into a text file, feeds file, extended CSV, and others using this format option, so that then you can share it with your colleagues or save it for later, or yeah, process it with other tools. And there's links to more details there and there. And some other things. So if you're mapping, right, you want to turn your grid of observations into a cube. There's a tool called the GVT Grider, which is a separate tool that we use for gridding Green Bank Observatory observations. It's command line based, so you go into a shell and you can type GVT Grider. It has a bunch of options like specify which channels to use, if you want to average a bunch of them, and where to save your outputs. And it will basically make a cube for you called, as we said, output my cube. It will be whatever you specify as the output underscore cube dot fits. That's the actual data, and then an underscore weight dot fits. Those are the weights. Yep, and you can open this with Casa Viewer or Carta or VS9 or Glue. I don't know what's popular out these days. There's also a tool called the GVT pipeline, which the idea was if you have mapping observations, this will basically take them, reduce them for you, and make you a cube. It's very basic, meaning the calibration that it applies, it's the very minimum. It works wonderful in some cases. So you're welcome to try it. And that's it. Yep. Sorry, I didn't leave time uh, for more questions, but yeah, please ask if you have any.
Thank you so much, Pedro. Like Pedro said, you're all the guinea pigs of this workshop using Dysh for the first time in a formal event from the observatory. So we are happy to take any of the feedback. We'll send out a survey after the workshop as well, where you can put any feedback in. And we are at the end of the first day. Congratulations and thank you for being here with us. You can just pop in tomorrow at 9 a.m. and we'll have breakout rooms for your groups. You'll be groups 3, 4, and 5. So whenever you start tomorrow, feel free just to find your breakout room and start planning your observations. So thank you very much. See you all tomorrow.
Thank
Thanks,
you.
everyone.
See you. Thank you.
Thank you. See you tomorrow.